So I'm very happy to have Professor Mung Chiang. How do you say it?
Chiang.
Chiang is fine. Yeah. Who's an assistant professor of electrical engineering at Princeton University. I actually first found out about him when I was looking at the seminar lists in the department, and it was the announcement for talks very similar to this. And I thought I would really like to listen to it. I'm really happy that he. Sorry about this. So I'm very happy that he agreed to come. So Mung has actually a long list of achievements and awards, and I'll just mention one or two of them. Before he joined. Excuse me. So let me turn it off. Sorry, I can't talk now. I'll call you back some other time. Okay, I'm sorry. Okay, let me turn it off. You know, they call at the most embarrassing times. Okay, so let me just mention one or two. So before he joined Princeton, he has already consulted at 3 telecom companies as system engineers. And 2 of his awards are Stanford University School of Engineering Terman Award and SBC Communications Incorporated New Technology Introduction Contribution Award. So without further ado, why don't you let him talk about it?
Thank you, Matt, for the kind invitation. Your cell phone ringing shows how proliferated is wireless communications these days, and it's anytime, anywhere, whether you like it or not. So today's talk is related, of course, to wireless networks. I'm very pleasured. It's given me a lot of pleasure to be here at WINLAB, one of the best places producing wireless research. Today's topic is on utility optimization in wireless networks, new challenges, recent advances, and open issues. So the framework of network utility maximization has been proliferated to a large set of problems over the last few years for primarily wired networks such as internet, and to some extent been extended to wireless cellular and alpha networks. So I'll briefly talk about the new challenges we have in doing this extension, and then present 4 recently developed algorithms on 4 different cases, including cellular and ad hoc formulations. In each of these cases, we'll present an algorithm, and we'll prove global and joint convergence to the optimal rate power joint allocation for the 4 different cases through these algorithms. And then we'll conclude with a brief discussion of some of the open issues and challenges. So before I start, I'd like to acknowledge a very helpful discussion on related topics with many people, including Nick Bambos, Jason Bell, Randy Berry, Stephen Boyd, Stephen Lowe, Peter Marbach, Dan O'Neill, Nat Shaw, Lin Xiao, and Emma Ye. So before we talk about wireless, let's start with utility maximization for wired network like the internet. And this problem, which is a simple optimization problem, turns out to provide a very rich set of framework to analyze many things. We're here maximizing a total network utility. It's a simple sum of each user indexed by S utility, where U sub S is assumed usually to be smooth, non-decreasing, and often concave, but not necessarily, and they are functions of the rates X sub S, allowed to be transmitted by user S, subject to simple linear flow constraint that says all the flows on each link indexed by L, that is, you sum over the range of all the sources, such that this link L looking at lies in the set of links used by source S. The total flow can be no greater than the provided quote-unquote capacity or attainable throughput on that link, called C sub L. Notice that we're only varying over the assigned rates. It's a rate allocation problem. For a given set of routing and for a given set of link throughput or quote-unquote capacities. This reflects a wired internet perspective. That is, you fix the link capacity and you only vary the source rate, vector x, in order to maximize some description, nonlinear description of how happy users would be, each end user, as a function of the rate allocation. And this perspective has been found a lot of applications, including two major streams of application. One is using this framework to understand distributed rate allocation, how to solve this problem, which is a nonlinear maximization over linear constraints in a distributive manner. In particular, congestion control protocols in TCP. Another stream of applications of this model is to model user behaviors, including selfish behaviors and the network efficiency. So let's take a look at this perspective in this talk. And there's been a lot of very interesting work since Caddy's groundbreaking paper in '98, including all these people, and this is, of course, only a partial list of people who are working on wired network utility optimization in order to understand TCP and distributed rate allocation. So let me provide a quick review on one of the most interesting applications coming out of this model, that is internet congestion control. So let's say this is, for now, a totally wired network with some source nodes in red and intermediate routers in green. And TCP in layer 4 of the SI stack does end-to-end congestion control in the late 1980s. And the essential idea is that each source doesn't know how much to pump to the network so that the link capacities are efficiently utilized and you do not induce congestion. So they try to probe the network congestion state using the sliding window W, which will evolve as a function of time t at each source. Most of the large file transfers spend their time in the so-called congestion avoidance phase, which is the phase that network utility maximization models. One variant, called TCP Vegas, is doing the following, according to the protocol description, that says each source would update its window size, which is proportional to the end-to-end throughput allowed, by looking at the difference between expect rate and actual rate. The expect rate is the rate without any queuing delay induced by congestion. And the actual rate is the empirical delay you observe round trip by measuring the timing of the acknowledgement packets. And in general, the timing or the lack of or the order of the acknowledgement packets in TCP is an indication of congestion. So if this difference is smaller than a certain fixed parameter alpha, then I'll increase my window size, otherwise I decrease it. So who generates these implicit signals of congestion? Well, each intermediate router would update the congestion signal, which can be viewed as a price, like in economics terms, a link price. Turns out in Vegas, people have recently shown that queuing delay is implicitly being used as the link price. So we can view this as each intermediate node updating the price, some kind of price, maybe queuing delay, of using that link, and is distributed, passed back to the sources using that link. And based on this signal, each source would update the window size. In a very interesting paper by Low, Peterson, Wang 2 years ago, they show that you can view this mechanism as a distributed primal-dual algorithm solving implicitly a global optimization problem. The sources and routers have no idea they're actually an optimizing machine. But you can view it in that way, and that leads you to a lot of machinery to rigorously analyze and further improve upon TCP. And in general, other variants of TCP have been analyzed over the past couple of years as implicitly solving a global optimization problem, which is precisely the problem we started with, the network utility maximization problem. Maximizing utility such that the total flow doesn't flood the available capacity on each link. But again, notice that the optimization variable to be distributively solved for only consists of the source rate vector load x, but not the link capacity vector load c, which are fixed as constants. So with ringtone, we come now to the wireless part. Now we would like to see that is it indeed true that these link capacities C are fixed numbers provided to you? It's not so in many cases, in particular not so in most wireless cases, because the link capacities are not a constant number, but depends on, as a function, on time-varying channel conditions, as well as adaptive resource allocation. The first you cannot control, the second you may be able to control. And such a dependency of the throughput on channel condition and resource allocation could be linear or non-linear. It could be pretty bad non-linearity, such as non-convex non-linearity. It could be a local or global dependency. We'll see the specific definition in a minute. And there could be even interference effects within the resource allocation schemes. In this talk, we'll be focusing on power control as the primary adaptive resource allocation mechanism, but it doesn't have to be. It could be adaptive modulation, adaptive choice of the interleaver depth. There are many other physical layer or MAC layer mechanisms. But we'll focus on power control. So now we view power control as a way to determine the data rate supply on each link, C. And the rate allocation is regulating the distributive user demands on their specific personal user rate reflected in the spectrum X. So now the challenge and opportunity is to maximize the network utility jointly over the solution space of rate allocation, X, and power control, P, which will impact C. This would lead to this generic structure of wireless network utility optimization over rates and powers. We still maximize the same old utility for the whole network, but subject to some much more general constraint on the joint solution space of rate vector R and power vector P. The question to be answered for 4 different formulations in this talk is how can we find, centralized or distributively, a global and jointly optimal R star P star to solve this problem. Of course, I have to specify what is this constraint set in each formulation.
The UIs are still concave in R?
The U in this talk will be assuming it is still a concave function of R, but there have been very recent extension to let it to be sigmoidal function, or in general, nonlinear and non-concave function. But for this talk, we'll stick to the standard, it's sometimes justified, sometimes not, assumption that U is concave function.
So your wireless network model here is one where you can think of each of these UIs as coming from a different user connected to a particular base station or something like that?
That's the general flavor. The specific formulation will vary as we go through some of the formulations. So you see the generic structure says that the utility is still locally and additively. These are some basic assumptions we are not varying. Depends on the user rates. It's only a function of the rates. But the link throughput now depends on the transmit powers. And how are the user rates and link throughput related to each other? Well, the user rates are constrained by the link throughput. Maybe each logical link is used only by one logical user, maybe by multiple at the same time. But in any case, it will be constrained by the link throughput, thus coupling user rates, link throughput, and transmit powers. Yes.
Why doesn't UI depend on power?
Right. So UI certainly can be explicitly depending on power. We're not doing that, not because it's invalid, it's just for the specific case I'll be talking about in this talk, we'll be focusing on that case. But it's implicitly depending on power for sure. It's not decoupled to problems. Because whatever your rate can be is constrained in the constraint set. And that constraint set is a joint constraint set on the pair of RT vector, as we'll see. Yes?
So you're not considering fairness.
Right. Fairness, again, can be either explicitly specified or implicitly. One way to implicitly specify that is through the shape of the utility function. For example, weighted log would imply to some definition of proportional fairness. And some parameterized family of utility function, all concave, leads to min-max fairness. So it can be described in that manner through the utility shapes that we are totally agnostic to. We can allow any concave utility shape.
But you don't penalize the fact that I have to use more power or less power.
Mm-hmm. Right, that again can be penalized here if you add another term in the objective function. In fact, that penalty mathematically doesn't present any new challenges. So the essential mathematical tool remains the same. And in any case, it is implicitly constrained in the constraint set.
So if you treat mutual interference, you would be through this constraint.
Yes. In fact, we're going through, in each case, I will specifically point out the specific formulation. This is a generic structure. So indeed, there are many variations on this theme. For example, what is the utility model? It could be just a flat identity function. U of R is whatever rate is. It could be a general concave function or general nonlinear function. This is the perspective we'll be taking in this particular talk. Now, the wireless link model, there can be many different ways to model each link dependency on the power. For example, it could be modeled as proportional to the log of 1 plus KSIR, where K is some function of the desired bit error rate and the specific modulation coding scheme. And it could be, for example, 1 over the gapped capacity. For simplicity's sake, in notation only, let's absorb this K factor into the SIR definition. So it could be log of 1 plus SIR. In the high SIR regime, or if you're using CDMA with high spreading gain codes, then it could be proportional to log of SIR. In some wideband regime, it could be proportional just to SIR in a linear manner. Or it could be proportional to some function of SIR, whereas this function is some success probability function, which usually is a sigmoidal function. Or you can take an information theoretic flavored definition. All these are assuming a specific set of modulation codes. You can ask what is the information theoretic fundamental bounds. But when we are coming to a slightly more complicated than the most trivial case, we'll see that we often do not know the answer to the information theoretic multi-terminal channel capacity region, with some few exceptions. So in that few exceptions, I'm going to actually show one case where this is the underlying model. But in other cases, I'll be using this model. Interference. Are there interference or not? In fact, we'll be looking at all three possible cases in different combinations in the four formulations. Either no interference, assuming the ideal case in a, say, single cell downlink, or with interference, where a signal-noise ratio becomes signal-interference ratio, or interference limited, that is, the interference term dominates the noise term in SIR. What about the network topology of this wireless network? Are we talking about we can be talking about a single hop, uplink or downlink, like in the cellular, or in the infrastructure-based LAN, the infrastructure-based LAN. We could be talking about a hybrid network with some wireless links and some wired links, and we can be talking about a multi-hop, all wireless network. And we'll be looking at formulations in all four cases here. But before I start looking into these four formulations, let me do justice to the vast literature on many of these topics. In particular, the issue of power control has been extensively investigated in the 90s by a number of people, including a number from WINLAB. And over the last couple of years, several years, have been work on the Nash equilibrium of power control gains, where people often find that the Nash equilibrium is not Pareto optimal. So we're going to take an optimization viewpoint, which is the viewpoint in this talk, with utility optimization framework through joint power control and something else. It could be base station selection, it could be rate control, it could be scheduling. Then there have been a sequence of interesting work over the last 3-4 years. In particular, the formulation 1 we're going to see in a minute is a variation of the Marbach-Berry model, where they look at linear dependency and we look at nonlinear dependency. And a very similar idea has been developed by O'Neill for our formulation 2. And this is, of course, by no means an exhaustive list. But in our case, this X for us is not our base station selection or scheduling. It is distributed rate control. So let's now start with 3 formulations. In the cellular case, it could be also, as I said, infrastructure mode, LAN. We look at no interference case, interference limited case, and the end-to-end case in a hybrid network. This is case 1, which is a very simple case, but there is a point to actually this simple case. Let's look at one cell, downlink base station to multiple wireless users. And let's assume that there is no interference or negligible interference effects on the data rate on each logical link here. So the base station has a total power P bar, which is going to be allocated to P sub I for receiver I. And the channel gain for each logical channel I is GI, the noise is NI, and the link model, as I said before, is proportional to log of SNR. Let's take this L proportionality constant to be 1 unit without loss of generality. And let's denote this big GI divided by big NI to be little GI. So SNR sub I for logical link I is GI PI. And here is the first problem we'll be dealing with. We maximize the total rate such that for each logical link I, the total rate on that link, well, here we're assuming there's a logical link per logical pair of transmitter receiver. So there's only 1 user per logical link, and per rate can be no greater than the attainable throughput on that link, which is a function of power P, but locally because of no interference assumption. So that's log SNRI. And the total power, because this is downlink broadcast, must be represented by total power P bar. And we're optimizing, as I said, the theme of this talk is optimizing jointly over P and R vectors. This is actually a very simple nonlinear, convex, and locally constrained optimization. So no big deal about this problem. You can solve this very easily in a centralized manner. What's interesting in the algorithm on the next slide is to see that, in fact, we can do a distributed algorithm to solve this problem with very fast convergence, where the base station does not need to know the utility function for each receiver, or the channel condition, that's the SNR for each receiver. And each receiver only needs to know his or her local utility and channel condition. And the interaction is all through a bidding process. So that's the algorithm. It's actually much simpler than it might appear on the slide. The essential idea is that after initialization, the base station keeps track of only the total bits, each bit denoted by lambda, from user J at iteration K. And the base station is a very dumb one. It only keeps track of the total bits, normalized by the total power P bar it has. And I call this normalized total bit I. It's just a number. And under the base station, I'm going to pass this number to you, and you, as a local receiver, would have local information on your own utility function and your own channel condition, GI. And you just solve a nonlinear equation where the variable, which is a scalar variable, is lambda sub I sub k plus 1. That's your bit in the next iteration, k sub plus 1. So this equation is a very simple one. It says that GI times lambda, your next bit, divided by exponential of the inverse of the first derivative of the utility function for yourself, where the argument is the variable, equal to a certain constant number for this iteration. And then you pass the solution as your next bit to the base station. And the base station just collects all the bits and then updates the total bit and pass the number to the next user. And next user gives the next bit, update the bits, and keep going. After one round is done for all the user, I have to come back to the first user. And of course, your question is, will this stop some point? And we will show it will stop at the optimal point. And when it stops, according to some finite stopping criteria, the power allocation will be proportional to the equilibrium price, normalized by the total price or the total bits multiplied by the total power.
So how is this related to? Isn't this sort of similar to what Berry did? Randall Berry?
Right. So I'm not sure which paper by Randy Berry you're referring to. So in particular, there's a paper by Berry, Randy Berry, and Peter Marbach in 2 years ago that talks about basically this problem, but they are assuming it's a wideband regime, and it's not a nonlinear relationship, it's a linear relationship. It turns out nonlinear is better than linear, because in the linear case, they are able to show in the Implicitly paper that you can do a sort of a distributed pricing mechanism,
right.
And it's suboptimal if you don't know the utility function at the base station, but it's asymptotically optimal as the number of users grows to infinity. It turns out, if you're assuming this log nonlinear dependency, turns out there will be some cancellation and simplification that allows you to say this is optimal even for a finite number of users. So nonlinearity actually is better than linearity of dependency. And indeed, that is captured in the theorem I'm going to show in the next slide. But let's just recap this pricing intuition. There will be 4 pricing intuitions, one for each case here. The first one is a very intuitive one that says the base station don't want to know the utility function and don't want to know the channel condition. Only knows his own total power, and each user will use his own local condition and utility to calculate the bits, and all the interaction are through the bidding price as lambda vector. This is sort of similar to Kelly's decomposition, which is for a wired internet, where you can decompose a rate allocation problem in this narrow utility maximization to one centralized problem and a whole bunch of distributed problems. The centralized problem doesn't need to know anything about the utility function's shape. And indeed, Berry and Marbach was trying to achieve the similar result for wireless no interference case. But it turns out nonlinear dependency will do the trick. But this bidding is an out-of-band bidding. That is, you are actually doing sort of a pilot training process here. And you better make sure this converges very fast before we can start using the right amount of power. So indeed, empirically, we see very fast convergence, but we don't know the exact speed of convergence. However, we are able to show that this algorithm will converge for any finite number of users to the jointly optimal power and rate that globally solves this wireless narrow utility maximization problem 1. In fact, there is a very technical condition for that to hold on self-concordance. Let's skip that, but suppose that technical condition doesn't satisfy for some rare cases, there is a modified version that will work, but slower. Well, let's look at a numerical example. I didn't show the topology here, but the topology is that there is one base station and 6 wireless users, and assuming some kind of concave utility and channel condition, and that base station doesn't know, this is the bidding evolution for user 1, 2, 3, 4, and 5 and 6 on the next slide. This is the bid starting at 0, 1, and then over time evolution. You see that the bids converges pretty fast, and that's users 5 and 6. And then after a few rounds of bidding iteration, this stops, and the resulting power and rate allocation for the 6 users are shown here. And we have much more extensive empirical numerical results that shows the speed of convergence empirically observed as a function of number of users, initial conditions, and so on and so forth. But that's not the point in this talk here. This just shows a numerical example. Well, we do not. Yes?
I've got a question. So who's getting more resources? The people with better channels or the people with worse channels?
It actually depends on intricate balance between each utility function and the channel condition. For example, suppose they're all using log utility, but someone uses all weighted log. If someone says, my weight is huge, then that's going to keep the balance, even if the channel condition is bad.
So suppose, let's say all of them have a similar utility function, say the identical one.
Yeah.
And if you had, so what can you say about this question? Versus, better channels versus worse channels.
Right. So the better channel will be assigned higher power. Right. But,
that's what I mean.
yeah, that's actually that's an interesting point. All right. So that's a very simple case. The point is to show this goal that people want to achieve, to replicate Kelly's new, seminal results, that decomposition results in utility function not needed at the base station. That's the point here. The optimization problem itself is a very simple one. This one is slightly more complicated. We're looking at case 2, at the interference limited, still cellular, so still single hop. But let's say there are 2 cells, multiple cells, and it could be uplink or downlink. The solid lines shows the intended transmission. The dotted lines shows the unintended interference. So indeed, we have to look at signal interference ratio instead of signal noise ratio. The SIR is the ratio between the received signal power, that's the transmit power, P sub I, at the transmitter on logical link I, times the path loss from the transmitter on logical link I to the receiver on logical link I, GII, which also incorporates spreading gain, if there is any. And the interference is a sum of all the interference signal Pj times Gij over log j not equal to I. Again, Gij is the signal, the path loss from the transmitter on logical link j to the receiver on logical link I, where I is not j. And notice we're taking away the noise. This is an interference limited case. And the link throughput is modeled as in a high spreading gain or high SRR regime as log of SIR, which is a function now globally dependent on the power vector P. And that's a key difference. This is not SNR sub I as a function of P sub I. This is a function of all the powers.
I have a quick question.
Yes.
So in Theorem 1, did you assume a certain order? You just assume the same, the log utility function for all of them, right? That's what you talked about for convergence. Can you go back to Theorem 1? When they asked the question, did you assume the same utility? You assume the same.
No. Utility can be any. It can be different. It doesn't matter. And the base station doesn't even know, have an idea of what your utility is.
Right, I understood that, but it's just you didn't assume the same similar function for
No, not at all. Not at all. Right. And utility model is distinct from the channel model. Utility model is a user behavior model, say, leading to fairness criteria, and this is a physical layer model.
So I guess the only thing you assumed to do is concave to prove any kind of convergence.
Yes. The non-concave is very interesting and challenging, and there are some very recent preliminary results, but again, that's not the point of this talk. So this log dependence is purely physical layer link throughput. It's got nothing to do with the utility model.
So the last case didn't have interference, or just...
No.
Okay.
No. Now we have interference. So now the problem looks similar, but it's quite different, actually. So still maximize the utility, but now on each logical link I, again, there's only one logical user per logical link because it's one hop. The rate can be no greater than the log of SIR, which is now a global function of P, the vector. And again, we're optimizing over the joint solution space of P and R. So ideally, of course, you would like to pick R to be very big, at least the R is a vector, so you want some entries of R to be big enough so that this is maximized, but the constraint says that the R's, each individual R cannot be greater than this number, and that number is a nonlinear and non-convex and global function of P vector. So how do we deal with this non-convex and global dependency? That's the gist of case 2. Let's first fix the notation following Kluskini-Mungenic and many later people as well. This diagonal matrix D, which is a function of the rate vector R, the diag of where each diagonal entry is e to the Ri divided by Gii, And there's a modified channel gain or channel loss matrix, G2D, where the off-diagonal entries are just Gij, and the diagonal entries are 0. That's by now standard notation. And algorithm 2, which is a centralized algorithm, is going to solve this problem too. So let's take a look at this algorithm 2. Again, it's actually simpler than what it might look like on the slide. You're given the channel gain matrix G and the utility function. Notice you do need to know the utility functions now, but they don't have to be the same shape. And the output you want is the optimal pairs of R star P star, which are coupled together. The algorithm says after initialization, you look at this matrix D, G2D, where D is a function of your current rate vector. You find the largest modulus eigenvalue, lambda, and the corresponding right and left eigenvalues. That's the Theorem eigenvalue and eigenvectors, right and left, of this matrix. Once you've got the P and Q's and lambda, you can compute a vector delta R, where each entry is 1 over Pi Qi times a normalized version of the first derivative of utility function, minus 1. And then you update your rate vector in the following two-step manner. First, you look at your current rate vector at iteration k, and then you add a scaled version where alpha is a constant positive step size times this delta R vector, that's R2D vector. Then you look at R2D, you subtract a vector consisting of ones, that's vector 1 transpose, and the scaling vector is a scalar. This doesn't look like a scalar. It's actually just a log of a number. That number is the Theorem eigenvalue of the matrix DG2D, where D now depends on R2D. And that is your updated rate vector. Once you've got updated rate vector, we reuse the same power update without any modification proposed by Foschini-Mugenic in 93, which can be written in the matrix notation as your next power vector is your current power vector, but left multiplied by dg2d, where d is a function of the updated rate vector. And then you are done. You've finished one round of the power and rate, in fact, rate first, and then power update. Then you compute the new eigenvalue and eigenvectors and keep going. Again, you would like to say, I'm going to stop at some time, and when I stop, I'm stopping at the globally and jointly optimal solution.
In the context of optimization theory, is this a standard algorithm which you accept?
No. I mean, there are some standard ways of thinking from optimization theory, but you need to specialize and simplify and tackle various kinds of transformation along the process. In particular, this is a nonlinear, non-convex, globally coupled optimization, which is one of the more difficult process of optimization. And if you're not careful enough with pre-processing before you start thinking about algorithm, and if you're not careful enough about the intermediate steps, you may easily end up with a locally optimal instead of global optimal solution.
Actually, that's exactly the point. I mean, your steps are pretty much local every time. What makes you sure that the result is...
Right. It's not that local. So local, there are two meanings of local. One is local optimality versus global optimality, which is optimization. Well, the other one is, this is talking about a local user instead of global wireless network. I don't know which one you're referring to.
About local optimality.
Okay, right. So, there are several tricks. The first one is that this nonlinear and non-convex problem, in fact, has a pseudo-non-convexity. That's the point I would like to drive at the end of the talk. That this non-convexity is so nice that a simple nonlinear one-to-one transformation will give you a nonlinear but convex optimization. And that's a key thing where local optimality becomes equivalent to global optimality.
So after some mapping, it becomes a convex optimization problem on a convex problem.
Yes. And that's a nonlinear but easy transformation. So, before again stating the theorem, let's look at the pricing intuition one more time. Turns out that the left Crump-Vini's eigenvector of this DG2D matrix, where D is a function of rate R, is a summary of interference effects on your rate power allocation problem. You can view that as an interference price. and the effective price to add more data rate to a user turns out to be the product of the power, the current power level, and the interference price. And the Theorem 2 we can prove, which is a longer proof, says the algorithm 2 converges to the jointly optimal power rate that globally solves this wireless network utility maximization problem 2. And furthermore, there's additional property that the convergence is monotonic, which will be compared with case 4 as we finish. And here's a numerical example. Again, the topology is a very simple one. There's one base station and 5 users. And we're looking at the uplink case in this case with a certain set of parameters describing the physical topology and fading environment. And this is the rate and this is the power adaptation, which are not monotonic. By monotonic, I mean is monotonic convergence in the objective function in the utility. But the powers and the rate and the powers as a function of time will evolve according to this computation. And the objective function in this case is a simple utility. It's just the sum rate, so it's the identity. And you see a monotonic rise in the objective function.
So for the second class of problems, there is no distributed analog, right?
Not yet.
You get the Nash equilibrium equilibrium.
Yes, not yet. In fact, there is one in case 4. Case 4 actually is more general than case 2, and it is distributed. But that one can be slowing convergence and it's not monotonic convergence. So yes, but not as nice as this monotonic convergence. And the pricing structure is totally different as well. So case 3. Now we're moving from single hop to multi-hop, but not quite. If we talk about wireless networks, ironically, or contrary to its name, a wireless network consists primarily of wired links. Not ad hoc case, not sensor network case, but in the network you are using actually day-to-day basis, the cellular network and the infrastructure node LAN is actually primarily wired link. There's usually only one or most 2 hops of wired links. And there's nothing wireless about a whole network in the rest of the connection end-to-end. So let's look at a hybrid network. There's a little addendum, there could be many, but let's say without loss generality, in fact. Well, one addendum, there's a wireless hop, could be uplink, could be downlink. That's the air interface part. And then this is a base station or access points, which will be connected by optic fiber, by twisted pair, by Ethernet cable to the backbone, which is wired. Of course, this wired network, PSTN or IP base, serves not just this wireless interface, it also serves many other sources. Connected, say, a server connected by Ethernet or connected by DSL. And there's nothing wireless about that source. But the backbone, some of the backbone links could be shared by both types of sources. So we call this a hybrid network consisting of wireless air interface and wired backbone. Turns out there is a trade-off, and that's the trade-off we would like to investigate. Between attaining the air interface capacity region boundary and avoiding congestion in the backbone. Because the key problem in the wireless case is that spectrum is expensive and scarce, and you would like to attain the capacity region's boundary if you can. But in the backbone, we are, again, assuming all the links are fixed capacity. This is a wide internet perspective. So the idea is that you cannot flood the available throughput on each link. Turns out there could be an interesting trade-off between the 2 competing objectives for the poor wireless sources. Now, the air interface could be multiple access channel or broadcast channel. We'll focus on the former MAC, but the methodology applies equally well to the broadcast channel case. And this is the case where we're going to actually use an information theoretic model here. We don't have to, we can still use the log 1 plus SR or log SIR case, but it just so happens that in this case we do know a nice information theoretic results. So let's take a look at what that would be. So this is a review slide on a known result by Dan Hanley in 98, where they look at a fading, Gaussian fading multiple access channel capacity region, and they show that The classical region consists of all the optimizers R star of the following problem, which, by the way, is on its own a joint optimization over rates and powers, just locally in that air interface. And that problem is maximizing, in fact, you can view this as a utility function as well. It's just a weighted identity utility function where mu are given weights, subject to a pretty interesting constraint that says all the rate vectors must belong to the unions of some sets, and each of these sets is described by a certain power vector p. The union is over all the feasible power vector p, subject to the peak and average power constraints. And the rate region consisting of all the rate vector r, such that if you look at any subset of these m transmitters in the MAC, their sum rate must be upper bounded by expectation over the fading process of half of log 1 plus 1 over sigma square noise Gaussian sum of hi pi, where pi are the power, as a function of the fading space h. And r and p must be non-negative. And furthermore, Zhe and Haney in the same 1998 paper provided a greedy rate and power allocation algorithm to computationally efficiently solve this problem, thus obtaining all the R star optimizer of the problem, thus obtaining the boundary of the capacity region. And in that allocation of rate and power algorithm, which I'm not going to go through, there's an interesting price as well. In addition to a rate reward vector mu, there's also a power price vector lambda that coordinates R and P vectors. And we'll see this coming up again soon in our slides. Alright, so that's just review. Now the question is as follows. Assume that you are one of these wirelessly connected users over here. And you actually got two prices. You have two bosses telling you different things to do possibly. One is the power price, which essentially is a local fading price. Local meaning local to the wireless air interface. That says that the fading process for you is bad at this time, so that if you want to attain some point on this back channel capacity region boundary, you should not be sending a lot of data because you are having a bad fading. But your end-to-end connection also passes some wired backbone links shared by many, many sources. And it may so happen that at this time your congestion price, say relayed to you by TCP feedback, says that the links you are using on your path is not highly congested. Your competitors are not sending a lot of data at this time. So this is your window of opportunity to send your data onto the backbone. What if you had a bad fading state and a good congestion state? Or the other way around. Or anywhere in between. Good and bad are relative. So we'd like to characterize this trade-off between attaining the MAC channel capacity region boundary and maximizing utility and avoiding congestion. And that's the problem formulation 3. We looked at the trade-off. And this is essentially a weighted sum of the objective functions. Here we're using S to index all the source nodes connected by some wire links to the backbone. And we're using I as the index of sources connected wirelessly to the backbone. And script L is a set of links shared by traffic from both types of sources. The objective is to maximize the utility function and to attain a point dictated by a given mu that would dictate the direction you strike toward the capacity region's boundary. And the theta is a given weight, how you care about the two competing objectives, subject to the following constraints. If a backbone link L is not in the script set, in the set script L, then it's just the standard normal constraint. Total flow cannot overflood link capacity. And this is not a wireless link, this is a wired link in the backbone. But if the link is shared by both types of traffic, then the wired sources and the wireless rates must add up to be no more than the link capacity in the wired backbone. And in the local case, the same constraint must be satisfied. Yes?
So what do you, do you think that Ri in the right is part of one of these utility functions? Is that how?
It could, it can, and you can actually also include that, but that won't actually make a technical difference. But in this case, let's say they are not. Let's say their utility is just identity. Okay, their utility is want to attain the capacity boundary.
But I guess if you don't combine the two types of utility, then your trade-off is going to depend on theta.
Certainly, the trade-off will depend on theta in any case, and we'll look at that theta effect in a minute.
So I guess the question, I try to reinterpret the question is that why can't you have some utility which is only concerning about the end-to-end connection, right? Part of it wireless, part of it wired, so that you don't have this theta.
Because in that case, you are not trying to solve the local channel capacity regions problem. Because this constraint doesn't capture everything. It is a constraint, but if you want to strike a point on the max channel capacity region boundary, which is shape, you need to pick an angle and draw the ray, and that angle is determined by the mu, and you draw the ray and reach a point on the boundary.
So I guess just to be obnoxious, why do I care about the air interface capacity? I mean, as a user, all I care about is the end-to-end.
Right. I mean, there are two answers to that. First of all, we are not favoring the wired user here. We are the total hybrid end-to-end system manager here. And two, because of that air interface part is using scarce and expensive spectrum resources. Therefore, we do not to be pointing at a very inferior and inefficient use of the spectrum, just because we want to avoid congestion at the backbone.
So I see. So you mean as a network manager,
right,
you are sort of making a moral judgment as to.
Right, I'm making moral judgment that one thing that I want to keep the wired user happy and everybody happy, but also I would like not to waste my expensive wireless spectrum at the wireless part. And this, you can set data to be 0. Right. So that would be a special case of this whole thing. So why don't we just be more general and solve the general problem? Yes.
Okay, here's a question. So I'm trying to understand the constraint, which is the third formula, the third line in your formula, which is the sum of two rates smaller than the CL, where L comes from the set of the shared links. So this is a link which has a wireless interface and a wired interface, right?
No, it doesn't have the wireless interface. It's a link in the backbone, but the traffic, end-to-end traffic using that link, some come from totally wired connected sources. Some actually comes from the wireless source.
Okay.
But that link itself, the two endpoints of that link doesn't have to be wireless. Okay. So now, this is algorithm 3 to solve that problem 3. What this means is that these 4 kinds of things are going on at the same time. Essentially, it's distributed, because now we're dealing not with one hop, there are many hops. So it's actually a very simple modification. Essentially, you just reuse the TCP congestion control. You don't want to reinvent the wheel, but you are using a modified utility function, mu prime. I'm sorry, prime was also used to denote derivative in the first 2 cases. Not derivative, is a modified utility, and it's the same utility if you're not interfering with the wired links, wireless links, but otherwise is a modified version. What are these alphas? These alpha are the key thing, the only key idea here, which is the coupling price. We'll see how that's updated. And then the max capacity problem is just solved in the same old way, but with a modified rate vector mu prime. Again, that's not derivative, it's a modified vector. This mu prime may become negative, because you're subtracting out the coupling price. But if not, you can use the Zhang-Greedy algorithm, which is a simple algorithm with low complexity. Otherwise, you have to use exponentially computationally intensive problem to solve this local problem. Now, how would you update the coupling price? That's the key here, right? Because you are using coupling price to change these to known mechanisms. Well, first of all, you update the unused capacity. I'm not writing down the iteration index time t here. Is implicit. So essentially, you just look at all the links shared, and then you look at how many bits per second are not used, and that's h. And then you do the following coupling price update. You update your current coupling price at time t on link L by subtracting out a beta, which is a positive constant, divided by the iteration number, times this unused capacity, and take the positive part, and that's your next coupling price at time t plus 1.
A quick question.
Yes.
So you are assuming a certain number of sources on your the wired network.
I'm assuming a what?
Certain number of sources.
Certain number, right? There will be a finite number of sources. Yeah. But they can have different shapes of utility, and they can be any finite number. So that's the algorithm, and the pricing intuition is the coupling price. So the coupling price, this alpha thing, if you're dealing with a coupled problem, there's bound to be some coupling price to couple it, and the coupling price just change the effective utility function and effective rate reward vector. It chooses the shape of your angle, and it chooses how happy you are. And that coupling price would in turn induce changes in the congestion pricing and the power pricing.
So this mu prime has an interpretation of the price as well or not?
Mu prime, no. Mu prime is the angle you strike in your mapped region. Yes.
So I'm trying to understand something sort of from physically how it happens, right?
Yeah.
Basically, you're saying that you sort of have two sorts of pressures. One is the pressure due to fading.
Yeah.
Right, and the other is the pressure due to basically a congestion
Yes.
on the backbone. But sort of my understanding of at least the way fading works and the congestion works, I don't know much about congestion on the backbone, right? That's why I'm asking this question. I thought these are at sort of distinctly different time scales.
Mm-hmm.
Because fading is something you sort of, think about it as something that is sort of small scale.
Mm-hmm.
Right? My understanding of the backbone pressure from TCP or something like that was usually sort of over a much longer window. If you think about bits as your units, right?
Mm-hmm.
It's going to be sort of on a
Right.
time scale that is sort of significantly much longer.
Certainly, yeah.
So,
the
so
time
how is
scales
this
are
interaction
different.
really-
Well, the
so is
congestion.
interaction really happening, or is it something just
Mm-hmm.
that is an artifact of your problem formulation?
Right. So that time scale, the congestion time scale, can be fast, can be slow. It highly depends on the mixture of the traffic and the size of the topology. But it certainly can be on a different time scale than the fading. So now, but the question here is that I'm just a user. I'm just looking at my local information to decide what to send, how much to send, and then I'm continuously feeding back with two sets of prices. One is this power price or fading price, and one is continuously updated congestion price. And to me, I have to decide. There is a conflict at any particular time instant. Whether time scale mix or not mix, there's no way for me to tell. But in any case, I need to make a decision: which one do I obey, or how much do I send? And that's the problem we're trying to do here. And I certainly concur that in general, it can be at a time different time scale globally in the network. But we're looking at what should for a wireless user do.
I guess your formulation is kind of one shot, right? Is that right? Like,
Yeah, it is. So
Yes,
given
it is.
two treasures, he's saying what to do exactly.
Right.
right.
Yeah.
Okay.
Yes.
It is.
Yes.
So that doesn't really matter.
So can it be that he's trying to, if, for example, the mobile decides to put more attention to the fading pressure,
Mhm.
and therefore the rates and traffic will vary on this time scale, which is extremely fast, would it cause the congestion actually to get some kind of an unstable phase so that the traditional congestion control methods just would fail?
Right. So the
So you're driving something
right.
which has a slow response time by a force which is rapidly changing, so it can cause all sorts of very bad things.
Right, so in fact, that's precisely what we're looking at now, which is the stability of the transient behavior over a sequence of time. But we haven't finished this one-shot deal yet, because we have to show that in this one-shot, this algorithm does solve the problem at that time. And indeed, this theorem we can prove says that algorithm 3 converges to the joint optimal powers and rates that globally solves the problem 3. And this theta, back to the question on theta, what theta you pick, theta is not an optimization variable, it's some weight, some favor that a system administrator will have to put. So you can certainly vary that, and by the complexity structure of the problem, that would mean that it would trace out the entire optimal trade-off curve for this time slot between the two objective functions if you vary your theta and solve the problem for each theta. So let's, I'm sorry that we're already exceeding the time limit.
We are relaxed about it.
Okay, that's good. So I'll keep on going for 3 more hours, and that'll bring me to dinner time. So the utility maximization in so far have been looked at is purely wireless, cellular case. Even though there is a backbone component in case 3, the backbone is not wireless, so it's still just cellular case. Now we look at a multi-hop all wireless case. So there is no more wired link, and there is a multi-hop transmission. And we are taking into both interference and noise. It's neither no interference nor interference limited, dominated. So the essential idea is that now each wireless source sends data along a route predetermined. We're not doing routing here, with multiple links, and each link shared by multiple sources. So let's just revisit our physical link model. Assume there's no base station, no access points, no cluster heads. And there's multi-hop transmission, but with fixed routing. And single path, meaning that each source only sends data along one path. It doesn't send data along multiple paths at the same time. And each logical link L here, the signal interference ratio is the signal divided by the interference plus the noise. And again, this GLL captures also spreading gain, there is any. And the link quote-unquote capacity, this attainable throughput, is a function of the power vector. And there's a proportionality constant times this log 1 plus KSIR, which we're going to say, due to high spreading gain, is approximated KSIR, and let's absorb this K into the definition of SIR. So push K into the definition of GLL here to simplify the notation. The key point is that this is still a function as a nonlinear, non-convex global function of the P vector for each link L. And thus we've derived as the last problem formulation. Maximize utility such that now the left-hand side in this constraint is no longer just one quantity. It's a summation of all the rates pumped from the wired sources I, summing over all the sources such that this link we're looking at on this constraint equation lies in the set of links used by this source. It's just a way to say the total flow, is no greater than the attainable throughput on that link as a function of P vector. And this holds for all the links. So now the sources are in red, intermediate nodes are in green, and of course this intermediate node can also become a source. And all the links are wireless. And again, we're trying to solve it in the joint solution space of var vector and P vector.
What is the link in this?
Right, link is a logical link. It is, for example, these two links could actually, could be same physical link. This two won't be, but it could be the same physical link, but if there are different logical connections, would be different. And the issue with this problem is that this is actually a more general formulation than problem 2 here. We're still dealing with nonlinear, non-convex dependency globally, and globally have two meanings here. One meaning is that the link throughput is a global function of P vector, and 2, we're summing over a range of indices I, so the powers and the rates are globally coupled. So if you will, you can say this is the rate allocation end-to-end changing the demand. This is the power allocation changing the supply, that is this quantity here. And demand can never be greater than the supply.
But you're assuming that your links from, say, one source to the destination is actually fixed before you start?
Yes. So the routes. So I'm a source.
LI is actually fixed for every I.
Yes. So we're assuming that we're not doing joint routing and power control and rate allocation. The routes are determined. So I can say a couple words about routes after this thing is done. So we would like to have a distributed algorithm to solve this problem. And the algorithm, for the algorithm, let's look at actually a side point, which is this actually presents an opportunity, new opportunity for congestion control. The current way to do congestion control in the internet is that you don't want to see bottleneck. So if you see a bottleneck building up, you implicitly tell all the sources using this bottleneck link that back off your rate, and that dissolves congestion. But if you can build in real time a fatter pipe and bring the queued packets out faster, that's another way to dissolve congestion without backing off at the sources. But you need to be able to put just the right amount of power at each transmitter so that it creates just the right configuration of interference globally, so that it just alleviates the global bandwidth bottleneck and dissolves congestion. Well, how do you know where is the bottleneck? It's dynamic changing, and that's a bottleneck with respect to the utility problem, right? And if you dissolve one bottleneck, say by increasing the power locally or reducing the power, interference power, even if you find a way to do that distributively, still you might be creating interference on other links. In fact, you will be, and you might be just creating new bottlenecks. So you're just shuffling your bottleneck here and there and here and there. At the end of the day, you may not increase or maximize your network utility. But there's a hope that maybe we can recycle the congestion price. The prices are now used by TCP to regulate demand. Suppose you recycle the same price and use it to balance supply and demand. Wouldn't that be nice?
What does that mean?
It means this. So what exactly does that mean? So this is Algorithm 4, and 4 things are going on at the same time. At each intermediate node, the queuing delay is implicitly updated as the queuing delay. Thus, the instantaneous difference at this time shot, the difference between the egress rate and ingress rate, divided by the power, and then scaled by a positive number constant gamma. And at each source, the window size is updated according to Vegas. It doesn't have to be Vegas, but let's, to be concrete, take Vegas. So the window size is related to the rate by this total delay. So essentially, this is just the expression I showed you earlier in the review slide, that small d is the end-to-end delay without queuing delay. Big D is the end-to-end delay with congestion-induced queuing delay, and alpha is a fixed parameter. Up to this point, nothing new. These are just standardized way to do TCP Vegas. Except this gamma is actually an improvement based on optimization theoretic analysis of it. But this is just TCP Vegas. Well, we have to do the power control part. The idea is as follows. Each wireless transmitter is going to measure some locally measurable quantities. I'm going to measure my local SIR, I'm going to measure my local queuing delay, scaled queuing delay, and I'm going to measure my local received power. Multiply them together, that gives me a number. I call this number a message M from me, J, at time T, and I pass that to all other transmitters. Say, well, that requires a flooding message passing, and which is not scalable. We'll talk about that in a minute. But in the ideal case, you will do a full-scale message passing by flooding, and each transmitter, upon receiving these little messages, all the numbers, will update its power on link, multi-link error from time t to t+1 in 2 ways. First, increase the power proportional to your local queuing delay and inverse proportional to your current power, where the constant is, proportionality constant is a positive number. Up. 2, subtract out a weighted sum of the messages you have collected at this time, where the weights are the path loss from the one who sent you the message to you. This turns out to be very helpful. We don't know this would be the case before we do it, but at the end of the day, it simplifies into this form. This is intuitive. It says that if you want to help yourself, long queuing delay, increase your power. But if you're already sending a lot of power, don't increase too much. If you want to help others, you should decrease your power. Now,
so this distributed power control sort of implicitly requires global visibility, right?
Right. It requires a message passing of a single number.
Right.
And that's where things get decoupled. actually, since I won't have time later on, so let me just mention that. But it turns out that this is very helpful. So the message are given some weights. It turns out the weights are the path loss. So if you're far, far away from me, I can just ignore it because, say, this is distance to the -4, distance to -3.5. So heuristic is to say, I only care about my close neighbor's message to me. The far neighbors, since will be weighted very little, I would just skip that. And then you have certain conditions under which this still would converge.
Why should the so first of all, the message is just the interference power I see, right? Scale by lambda j.
Yep.
Right, and so why should I scale it with lambda j?
That's I don't know why. After deriving it, it shows up like this. But you see that you need lambda j some manner. Because without the lambda j, how would you know? The whole idea is to lambda j is the actually that's answering your earlier question. Lambda j is the congestion price.
Right.
Now you are doing the power control in the physical layer and end-to-end rate control in the transport layer, and the lambdas you want sort of a layering price, right? So to balance supply and demand, and we're recycling the same lambda that's generated. Lambda has to appear somewhere because otherwise you are just doing two separate things. Somewhere you have to take a peek at what's going on with your rate allocations, in fact. It just turns out lambda appears in a simple way like this. So the Theorem Four, we can prove, says that under some condition, algorithm 4 converges to the jointly optimal powers and rates that globally solves the wireless network. Utility maximization problem 4. The conditions are that finite powers and buffer sizes, and strictly positive powers, which is very benign assumptions, because if the power is absolutely zero, then it's just powered off node. And for small enough gamma and kappa, we see actually we have some results on how small is small. Then algorithm 4 converges to the joint global solution. But you may say, well, if you have this, why did you bother to show us case 2? This is actually more general than case 2. Because the convergence in this case is not monotonic and it can be slow. That's sort of the price you have to pay with distributive methods. Here's a little numerical example. You have a very simple topology, data topology. Yes. No problem.
So when you say assume finite powers, what is it that sort of? Okay, these are conditions that you impose, then you're able to show convergence, right?
Right. If you have infinite power, right?
Yeah, but at the outset, if you sort of just set up the, say, throw down a topology, right? Randomly sort of throw down these people and make them do this.
Yep.
There can be situations where the powers can just blow up, right?
As long as it could be very large.
I mean, so if you don't have, let's say, a max power constraint.
Right, it can be very large.
It is possible for the algorithm to blow up, isn't it?
The algorithm will actually converge slower if the larger power becomes, actually. But as long as it's a finite but large number, it can be 1 billion watts. You can use, large amount of power. As long as it's not infinite, then convergence.
I guess let me rephrase the question.
Yes.
Can your system become infeasible? That's what I'm asking. See, if your system is infeasible, right, then sort of if you typically think about distributed power control. Right. The powers, all these powers.
No, they actually won't be infeasible. No, it will not be infeasible. In fact, the algorithm is a primal and dual feasible algorithm, so it will always be feasible.
Even if you allow infinite power.
No, it can be power can increase. Power can increase, but since the feasibility here requires rate and power, so you can change your rate. You can change your power. I can change my rates, and I can make sure it's a feasible optimization problem. Still lies in the feasible solutions there. Right. But for convergence, you cannot tolerate infinite power. Because as you can see, obviously, if you allow some infinite quantity here, things can get bad.
So it's basically tragedy of the commons, right? If you allow infinite power, that would be cases
right. So let me make sure that infinite power is an assumption that's a mathematical technicality here. In reality, you never have exactly infinite power. And in reality, actually, you don't care about convergence in the absolute sense. You're going to stop at a finite time anyway. So that's purely a mathematical technicality that infinite power is no good for convergence.
No. I think the issue was not really infinite. It was more of feasibility.
Right. Yeah. Feasibility is yes.
That's the issue. Really.
Okay. So back to this numerical example, which is very small, but suffices to illustrate the point. In fact, the point of the whole, every 4 cases here. while longitude rate and joint rate and power allocation. So there are 4 end-to-end connections, and they have different links are used differently. And there are certain physical topologies here that I'm not putting down the parameters. Your first one, TCP Vegas, with no power control, and let it reach equilibrium. Then at time 0, you kick in the power control part, and then the powers adapt themselves distributively, and that changes the link data rate because it's simple topology, it follows pretty much. And it's essentially trying to equalize the queuing delay, which is intuitive. You don't want to bottleneck. But you don't get exactly equalized queuing delay because of different loads and different utility shapes. I didn't say the utility, they're all weighted log because it's Vegas. And at the end of the day, the end-to-end throughput for the 4 end-to-end connections increases after convergence. But more importantly, we look at the end-to-end throughput per watt of power you use. And that's the sort of energy efficiency. And then that sees 82% increase, which is a typical number in this kind of scale of topology. And most of the benefits, if you run it on the much larger ones, can come from a limited message passing. Limited message passing meaning that I don't wait for the message from far away neighbor. It may not converge. There is a certain sufficient condition under which that would converge. But the idea is that you put the right power, the right spot, that helps you with 2 things. One, you don't waste your power. That helps with your power energy efficiency. And 2, you try to collaborate distributively to create the best interference configuration so that according to the current load and utility function, you achieve the maximized network utility. And again, there's a pricing intuition as well. That is the same pricing for TCP, that you use prices to regulate demand. But now we add a new module, that's the power control module. And the power control will change the supply, that's the link throughput, which will change the dynamics of TCP, which will in turn changes through the shadow price updates of the power update, thus forming a joint and global nonlinear dynamical system. And Theorem 4 says that this nonlinear dynamical system would converge to the joint global finality. And see that there is a clear cut between the existing TCP congestion control and link queue update algorithm. You don't need to break this. All you need to do is to take a peek at the prices that's already being generated and use that to smartly allocate your power in the physical layer. So in this case, it turns out congestion price is also the layering price. And as I said, by the way, we're approaching the end, so thank you for your patience. There are other properties we can talk about here. It's not just about convergence, it's also about robustness, say against channel estimation error, say all these GIJs, and the fading. Maybe your packet gets lost because of fading, so you're using the wrong price to update your source. We have certain sufficient condition under which it will converge to the right thing, even with these. Thus, convergence with asynchronized message passing, no one has the same clock, and there will be propagation delays. We have a sufficient condition for that. Sufficient condition for partial message passing to work to convergence, work to the right point. Some loose bounds on the rate of convergence, some way to speed up the convergence and choose the appropriate constant parameters and so on. But let me skip all those additional properties and show just within 1 or 2 slides what goes behind the theorems. I didn't say a word about the proof. The idea as follows. This is the essential idea that you can view all these different things, different formulation, as sort of a unified in the optimization theoretic framework, and it's in fact part of the broad development of optimization theoretic framework of network design in general. The key idea behind algorithm 1, theorem 1, is to utilize the special structure of the Lagrange view problem to decouple the mobile from the base station. Key idea behind theorem 2 is Perron-Fini's theory of nonlinear matrices will help you to characterize the KKT condition in a nice way. Key idea behind theorem 3 is the partial Lagrangian decomposition and subgradient. Key idea behind theorem 4 is the partial Lagrangian decomposition and the distributed gradient descent by message passing. So that's the key idea, and then you of course need to fill in the details. And in general, the key idea is convexity or pseudo-non-convexity and duality are important in all the cases. And certainly the pricing interpretation manifest themselves in all formulations. We've seen the bidding price in low interference case, interference price in the interference limited case, coupling price in the hybrid case, layering price in the cross-layer for ad hoc network case. And we see that these are equivalent or sometimes functions of known two classes prices, conventional price in network control and prior price in information theory. I know you are eager to stop, but let me advertise my new course. This is a commercial that I'm developing and teaching a new graduate course at Princeton called Optimization of Communication Systems, Methodologies, Applications. 50% on methodologies, centered around convex optimization, but including other classical results. 50% on applications, or interleaved together. That's John, curriculum development with Stephen Lowe at Caltech, and contribution from many friends. It's an evolving course, so please send me your feedback information. All the 24 lecture notes, which have already been done, first round has been put on our website, this URL. Covers cost, recent results on optimization, nonlinear, framework for various aspects of communication systems, some information theory problems, communication theory, signal processing algorithms, detection estimation, internet protocols, network modeling control, wireless network resource allocation, both classic and recent results.
So when are you offering this?
This is actually a spring. I've just finished teaching the first round of it. So all the 24 lectures are on this website now, with typos and not enough figures, graphs. And it's an evolving course. The application topic, recent results,